You are welcome again. This is your channel Zion Tutor, where we deal with Cambridge syllabus, IGCSE maths, additional maths, A-level maths. And today, we want to look at an aspect of AS mathematics under quadratic equation. And the two things we want to check there today is how we use your quadratic formula to determine the nature of roots and how we use it to solve problems relating to intersection of a quadratic curve and a line. So without wasting much of our time, let's delve into the topic. Now, when we are talking about a quadratic equation is an equation of this form. Equation of the form ax squared plus bx plus c equals to 0. This is a quadratic equation. But if we remove this equals to, it becomes an expression. But it's from this quadratic equation that we generate the quadratic formula. If you can see here, the coefficient of our x squared is a, the coefficient of x is b, and our constant term here is c. So from here, we know our quadratic formula is x, since it's the variable we use, is minus b plus or minus square root of b squared minus 4ac, everything divided by 2a. Is our quadratic formula. And there's an aspect of this formula that we need to use, which is this one inside the square root, b squared minus 4ac. We call it a discriminant. And we represent it with this, a discriminant d. So if discriminant d is equals to b squared minus 4ac. So this is what we use to determine the nature of roots. This is what we use to determine the nature of roots. So now the first one we want to check is that if d is equals to 0, that means for our discriminant is equals to 0, we are trying to say b squared minus 4ac equals 0. So that means this square root becomes 0, and the value for our x is minus b over 2a. So that means this now saying we have a real and equal root. We have real and equal roots. We can also say it's a repeated root. A repeated root. But don't forget it's real. It's real. Because we can find it on a real line. So that means if our d equals to 0, we have it as real and equal roots. Now the second thing is if our d is greater than 0, so we are saying b squared minus 4ac is greater than 0. Is greater than 0. So that means that this square root, the value of this square root here is positive. Is positive, so that we can really find the square root. And once that is positive, what we are actually saying is that we have what we call a real and distinct root. We have real and distinct root. So that we have a real and distinct root. We have real and distinct root when our discriminant is greater than 0. And the third part of it is if d is less than 0. We are saying b squared minus 4ac is less than 0. So what we are actually saying is that this square root here, this square root becomes a negative. And once you have a negative, that means it has left the shore of a real number. It has now become a complex number. So it is not real again. That means it can become a complex number. So when our d is less than 0, you see we have no real roots. So it becomes complex. It becomes a complex number. So those are the three natures of roots. If our d is equals to 0, we have what we call an equal real root or a repeated root. If our d is greater than 0, we have a real and two distinct roots, a distinct root. But if our d is less than 0, there is no real root there. We have what we call a complex root. Let's go to the, now if you look at this, now, sorry about that. If you look at this, it's just a summary of what you have been saying. It's a summary. It's a summary. The nature of roots. It's a summary of what we have been saying. If we check this now, that means we are saying that when d is greater than 0, we have real and distinct roots. But now this will now simplify it further. That when we find our d and d is a perfect square, then we have a rational root. And what we mean by rational, that means we can write it as a fraction or as a whole number. Now, every whole number, every natural number can be written as a fraction. 1 can be written as 1 over 1. 2 can be written as 2 over 1. But if d is not a perfect square, we have what we call a rational root. So that means this is a point we get a decimal point, like that. So that means the second aspect is when d is equals to 0, we have what we call real and equal roots, real and equal roots. And the third aspect is when d is less than 0, we have a complex. It's a complex root. There we have what we call a complex conjugate. And that is a complex, it's a complex root. It's a complex root. Now, let's try to view it graphically. Now, you can see graphically now that when our d is equals to 0, is equals to 0, we say we have a real and equal root. You will see the graph. Anytime you see any quadratic graph that comes to a point on your x-axis, which is the root of the equation, and turn from that point, it says that that value at this point now is occurred twice. Occur twice. It occurs twice. It occurred twice. It occurred twice. That is it. It occurred twice. So sorry. That means it occurred twice. It occurred twice. You see that place. And anytime our d is greater than 0, anytime our d is greater than 0, this point, we have to call it two distinct trees. You see that the graph, it cuts our x-axis at two distinct points. At two distinct points. This is the graph. At two distinct points. And when it's less than 0, that means it's not real. That's when we have a floating graph. It does not cut the x-axis at any point. We have a floating graph. This is how to view it graphically using our discriminants. Now let's move to the second part of using this nature of roots. Now let's look at this. Now look at this now. We have the nature of roots, we have a line and a curve. We are trying to use the nature of roots to also solve a problem that relates line and a curve. What we're actually saying is that once we say b squared minus 4ac is greater than 0, don't forget the nature of root, we say it's two distinct roots. It's two distinct roots. But what actually happens is that when you have a line that intersects a quadratic curve at two distinct points or at 2 points, we can use this discriminant b squared minus 4ac to solve that problem. This is the graph underneath. You see, these are quadratic curve and a line cuts it at two distinct points, So in any situation when we have a problem saying that a curve, quadratic curve, and a line intersect at two distinct points, so what we are trying to say there is that in solving that problem, we need to come and use our discriminant that says b squared minus 4ac is greater than 0. Now, the second part of it is that when our discriminant is equals to 0, So this is what we say our discriminant is equals to 0, when b squared minus 4ac is equals to 0. Now, don't forget in our nature of root, we say we have two equal roots, I would say repeated roots. Now, what this means in line and curve is that we have a line that meets the curve at a point. And when a line meets a curve at a point, you see that line is a tangent, a line of tangent. So when there is an intersection between a quadratic curve and a line of tangent, that means it meets at a point. The discriminant to use in solving that problem is b squared minus 4ac. b squared minus 4ac. And the third thing is, when we have no real roots, you know the thing is floating, the graph is floating in our no real root. When we say b squared minus 4ac is less than 0, what we actually means here is there is no point of intersection. No point of intersection. You can see the graph. There is no point of intersection. But in solving something related to this, we need to first assume that the line intersects by equating the y of the quadratic curve and y of the equation of the line. I will use this discriminant of b squared minus 4ac is less than 0. Is less than 0. Now, let's delve into some questions so we can see the benefit of these things. Now, the first question here is saying that an equation of a curve is y equals to 4x squared minus kx plus half a squared. And the equation of the line, this is the equation of our curve. You see the highest power here is 2, so it's a quadratic curve. And now this our line here is a linear one where k and a are constant. Now, if you look at the question A, it says given that the curve and the line intersect at the point with x coordinates 0 and 3/4. That means when the line and the curve intersect, the x coordinate at that point is 0 and 3/4. You find the values of k and a. Don't forget, when we have a curve and the line intersecting, the y coordinate at that point of the curve will be equals to the y coordinates at that point of the line, at that point of intersection. What we are actually saying is that we say 4x squared, which is our curve, minus kx plus half k squared is equals to the y of the line. That means we are saying x minus a. That's what we mean by when the curve and the line intersect. Now, but the question is given at that point of intersection, the x coordinates is 0 and 3/4. What does that mean? That means we are saying when our x coordinate is equals to 0, what does this equation turns to? So we substitute 0 into this. This 4x squared becomes 0, and this ks becomes 0 because 0 multiplied by k is 0, 0 multiplied by 4 will give us 0, and the x here becomes 0. So that means in this we are left with half k squared is equals to minus a. Let's keep this as equation 1. Now, at a point, our x is equals to 3 over 4. That means if we substitute 3 over 4 into that equation of intersection, we have 4 into brackets 3 over 4 whole square minus 3 over 4k plus half k square be equals to 3 over 4 minus a. And don't forget from our equation 1, half k square is equals to minus a. So by simplifying this further, this becomes 9 over 4 minus 3k over 4. Now this becomes minus a, which is now equals to 3 over 4 minus a. So now, if you collect like terms here, if you take a out, we see that a becomes 0, minus a plus a becomes 0. So we are left with 9 over 4 minus 3k over 4 equals to 3 over 4. Let's collect like terms by bringing this 3 over 4 in and take this one out. That means 9 over 4 minus 3 over 4 equals to 3k over 4. By finding the LCM and simplifying this order, this becomes 6 over 4 equals to 3k over 4. So if the denominator is equal, that means the numerator also will be equal. That means we're saying 6 equals to 3k. And by so doing, divide both sides by 3, we get our k to be 2. So we know our k is 2. And don't forget in our equation 1, we say half k squared equals to minus a. So from there, we can get our a. We can get our a. We can get our a. Don't forget, we say half k squared equals to minus a. That means half 2 squared equals to minus a. So that means 2 equals to minus a. Invariably, we can say a is equals to minus 2. So that means our k equals to 2 and a equals to minus 2. That's the first problem there. That's the first. On the a there, you say we should find the values of k and a. So we are able to find that. And the b part is now saying, given instead that a equals to minus 7. Now, if you look at this, now means we are not using the a we get. We have been given another a. Find the values of k for which the line is a tangent to the curve. Now, don't forget now, from line and curve intersection, a tangent is a line that meets a curve at a point, at a single point. And once we know that, that means the discriminant we use to solve that problem is b squared minus 4ac equals to 0. Don't let us forget that from our previous slide. Don't let us forget that. It needs to, these are things we need to check. It says the line is a tangent. So we know the point of intersection. A tangent meets the curve at a point. That means we are rewriting our equation of intersection and trying to put the value of a inside. And from there, we can use so what we actually, don't forget our equation of intersection of 4x squared minus kx plus half k squared equals to x minus a equals to x minus a equals to x minus a. Now, when we now say a equals to minus 7 over 2, so that means we are saying 4x squared minus kx plus half k squared equals to x now becomes plus 7 over 2. Let's collect like times to make the equation look like a quadratic equation. Which means that we want to make sure that it's equals to 0. We want to turn everything at this side in. So that means we have what we call 4x squared minus kx. If I bring x in, it becomes minus x plus half k squared minus 7 over 2 becomes 0. Now let's factorize for that to make it look like quadratic equation proper. That means we have 4x squared. If I say plus x into brackets, what's common there? We have minus k minus 1 plus, if I factorize this further, this one becomes k squared minus 7 all divided by 2 equals to 0. From that, we will be able to get our a, b, and c because the coefficient of x squared is our a, that means our a is 4. The coefficient of x is our b, that means minus k minus 1. And the constant term, k squared minus 7 divided by 2 is our c. So that means we are saying our a is equals to 4, b is equals to minus k minus 1, and c equals to k squared minus 7 divided by 2. So we know that the line meets the curve at a point. So that means our discriminant b squared is 4ac equals to 0. Let's substitute it. We have minus k minus 1 all squared minus 4 into bracket a is also 4 into bracket c k squared minus 7 over 2 close bracket equals 0. So if we simplify this further, this gives k squared plus 2k plus 1. Here 2 here 1, you can say 2 here to be 2 minus 2 times 4, that's minus 8 multiplied by k. We have minus 8k squared minus 8 multiplied by minus 7, that's plus 56 equals 0. So by collecting like times, we have k squared minus 8k squared becomes minus 7k squared plus 2k plus 1 plus 56 becomes plus 57 equals 0. So if I want to remove the negative in front of our 7k squared and multiply it by minus 1, that means everything I want to multiply it by minus 1. So remove that, that becomes 7k squared minus 2k minus 57 equals 0. And this is a quadratic equation. Either we solve it by using the quadratic formula or we solve it by factorization method. Either way we do, which we have done in our previous class and slide. So that means we find out that from here, k equals 3, and also k will be equals to minus 19 over 7. K equals 3, and k will be equals to minus 19 over 7. So the question says that we should find the values of k. Is it given instead that a equals this? Find the values of k for which this line is a tangent. So the values of k are, we have two values, that means 3 minus 19 over 7. 3 and minus 19 over 7. So when we are told to find an intersection, when you have an intersection of a tangent, the line that is a tangent to the curve, it meets at a point. Or if the line does not meet at a point, that means if it cuts a curve at two distinct points, we have it different. We have to use another. If you look at this is another problem under that. We have a line as an equation y equals to 2cx plus 3, and a curve as an equation cx squared plus 3x minus c, where c is a constant. Now, this one is not showing all necessary working. Determine which of these following statements is correct. Now, the line and the curve intersect only for a particular, but we know it intersects. The option B says the line and the curve intersect also. The question says the line and the curve do not intersect. option A, B, C requires us to solve it in the same format, but at the end of the day, we just want to know if they intersect. We know at two distinct points or more than the values of C, they say the set of values of C of all values of T, either it is greater than 0 or less than 0, or we are still following the same process. So at point of intersection, what we are actually saying, the y of the curve, quadratic curve, equals to the y of the line. That's the point of intersection. And what that means is we are saying that cx squared plus 3x minus c will be equals to the line 2cx plus 3. In this kind of problem, we need to, don't forget, collect like terms and make it look like a quadratic equation. So we have cx squared plus 3x minus 2cx minus c minus 3 becomes 0. So let's factorize further to make it look like quadratic equation prosper. Proper cx squared plus x into brackets 3 minus 2c minus c minus 3 equals to 0. So here now we know that our A equals to C, B equals to 3 minus 2C, and C of the discriminants, not this equation now, is equals to minus C minus 3. Now, every of the option B, A, B, C, we follow us using this discriminant B squared minus 4AC. Either it is now greater than 0 or less than 0, we don't know yet. But let's first evaluate this B squared minus 4AC, and we now later find out which option is correct. So that means we are saying when we substitute, we are saying 3 minus 2C all squared minus 4 into brackets A, C, and C is minus C minus 3. C is minus 2 minus 3. So if we factorize this further, we have what we call 9 minus 12. If we expand it, plus 4C squared. This one is minus 4C into bracket minus C minus 3. Minus C minus 3. So that means if we furthermore, we say our 9 minus 12C plus 4C squared. If you look, when we expand minus 4C, minus 4C times minus C, that becomes plus 4C squared, and that becomes plus 12C. So that will become plus 4C squared plus 12C. If we collect like that, we have 9 minus 12C plus 12C plus 8C squared. So we have 9 plus 8C squared. So now let's write it properly. 8C squared plus 9. If I now go to the option now, I'm now saying that the line and the curve intersect only for a particular set of values of C. That means for a particular set of values for C, let's check particular set of values for C. That means there is a particular set of values for C. This cannot work for this because this equation will work for all values of C. Because for all values of C, 8 squared plus 8C squared plus 9 will always be greater than 0. Now, because the power there is C squared, so no matter what the values of C is, either it's a positive integer or a negative integer, all will become positive. Because if we say minus 4 squared, we give me 16. If we say if it is positive 4 squared, so the square of any number will always come out positive. And once this comes out positive, we multiply it by 8, it's still positive. Add it by 9, add it to 9, it's still a positive value. If we say from sets of values of C, we not completely capture the solution. That means 8 squared, 8C squared plus 9 is greater than, will always be greater than 0. And this work for all set of values of C, for all values of C, all values of C, all values of C, all values of C. So if you look at the options, option A says the line and the curve intersect only for a particular set of values of C. No. The line and the curve intersect for all values of C. So that means our B here, B is our option. The line, no, the line intersects for all values of C, for all values of C. Comes to the end of the class for today. We appreciate you. Please, if you have any questions, relate it to the appropriate channel, and we communicate from there. We communicate from there. Thank you for staying with us. Thank you for staying with us.